Assalamualaikum and hi. We are from class DMK 4A want to present about characteristic of DC motor. This slide prepared by Nur Najlaa Safia binti Norizan and Nur Ainaa Izzati binti Zulkifli. This slide prepared for our beloved lecturer Muhammad Fauzi bin Anwar. What you will learn about characteristic of DC motor is speed torque curve and motor braking. Speed torque curve. First, in order to effectively design with DC motors, it is necessary to understand their characteristic curve. Second, for every motor, there is a specific torque speed curve and power curve. The graph beside shows a torque speed curve of a typical DC motor. Note that torque is inversely proportional to the speed of the output shaft. In other words, there is a trade-off between how much torque a motor delivers and how fast the output shaft spins. Motor characteristics are frequently given as 2 points in this graph. A. The stall torque as a TS represents the point on the graph at which the torque is a maximum but the shaft is not rotating. B. The no-load speed as a WN is the maximum output speed of the motor when no torque is applied to the output shaft. The formula of under steady condition is Vt equal to torque Ra divide torque constant plus voltage constant speed. This equation forms a linear relationship between the generated torque and velocity. This figure shows that linear relationship governing the torque speed characteristic of DC motor. We have speed equal to negative Vt divide voltage constant, torque armature resistance divide torque constant multiply voltage constant. If torque equal to 0, we have no load speed equal to Vt over voltage constant. If speed equal to 0, we have stall torque equal to torque constant multiply Vt divide armature resistance Ra, where speed no load is the no load speed and torque speed is the stall torque. For the example, a DC permanent magnet motor has the following parameters. Torque constant as Kt equal to 0.078 Nm/A. Voltage constant as Ke equal to 8.168 mV/rpm. Armature resistance as a Ra equal to 1.5 ohm. Rotor inertia as J equal to 0.45 kg. It draws 0.04 A. Calculate 1. The stall torque. 2. The no load speed. 3. The torque at 1500 rpm. For the solution, voltage constant equal to 8.168 millivolt rpm equal to 8.168 divide 1000 multiply 60 divide 2 pi equal to 0.078 volt or second. 8.168 divide 1000 because we want to change the unit from millivolt to volt. For the solution number 1, stop torque speed equal to 0, Ia equal to 24 divide armature resistance equal to 24 divide 1.5 equal to 16 A. Stall torque equal to torque constant multiply current equal to 0.078 multiply 16 equal to 1.048 Nm. At the solution number 2, at no load, current equal to 0.04 ampere, EA equal to Vt minus current multiply armature resistance equal to 24 minus 1.5 multiply 0.04 equal to 23.94 volt. Since EA equal to voltage constant speed equal to EA divide voltage constant equal 23.94 divide 0.078 equal to 306.9 equal to 2931 RPM. For the solution number 3, at 1500 RPM, speed equal to 157.1 second, EA equal to voltage constant multiply speed equal to 0.078 multiply 157.1. So it will be 12.25 volt, while the current equal to 24 minus EA divide armature resistance equal to 7.83 ampere. Lastly, torque equal to torque constant multiply current equal to 0.078 multiply 7.83 and it will be 0.61 Newton. Motor braking. First, stopping a DC motor could be a tiresome journey. Second, when a large DC motor is coupled to a heavy inertial load, it may take an hour or more for the system to come to a halt. Next, one way to get a rapid braking is by applying a simple mechanical friction. Next, a more elegant method is to circulate a reverse current in the armature. Next, coupled with a rotating momentum, it will induce a force to oppose the motion. Such is called electromechanical braking. Two source methods we will be studied. First, dynamic braking, and 2, plugging.
So, I will be explaining about dynamic braking. Dynamic braking allows to brake a motor by reversing the torque's direction. With brake, it essentially disconnects the running motor from its power source. The motor's rotor will then begin to rotate due to inactivity, thus functioning as a generator. At this point, the torque and the flow of the current are reversed, which causes the motor to come to a stop. How does dynamic braking work with a DC motor? When you detach electric motors from their power supplies, it generally has no problem stopping. However, a large motor, stopping will take longer. A large motor has a high amount of rotating inertia, as the stored energy must be dissolved through wind friction. However, with dynamic brake, you can improve this situation by making the motor operate like a generator. When the rotor acts like a generator, the torque is reversed. In this situation, a dynamic brake will force the torque that is going opposite of the rotation path to go to on the shaft. This will help the device to come to a rapid stop. Also, the motor will dissipate as a result of the resistance of the braking process. This process of dynamic braking comes in handy for applications such as conveyor belts, pumps, and fans. So next, I will be explaining about the detail of dynamic braking. Consider this is the DC shunt in the diagram and consider the motor is running in the forward mode and armature current. If switch A are suddenly thrown open, the supply is cut off and the motor will moderately come to a rest owing to friction and wind age. This process is termed as coasting because the field is still excited, continues to exist but falling at the same rate as the speed. If switch B closed upon opening switch A, the armature is suddenly connected to an external resistor, therefore producing an armature current which flows opposite IA1. This produces a reverse torque that brings the motor to a rapid but a very smooth stop. The dynamic of regenerative braking is an insufficient method of braking because all energy which is generated is dissipated in the form of heat in the resistor. Through proper electronics, this energy can actually be channeled back to the source. This method of braking, whereby energy from the motor is returned to the source during braking, sometimes called regenerative braking. As an additional information, during my research about dynamic braking, also known as regenerative braking in the module, but in the internet, it wrote dynamic braking is also known as rheostatic braking. Next are advantages and disadvantages of dynamic braking. First, this is much used method where an electric motor is worked as a generator once it is detached from the power source. In this braking, the energy which is stored will dissipate through the resistance of braking and other components used in the circuit. Third, this will reduce braking components based on wear on friction, and regeneration reduces the usage of. So next, I will be continuing to explain about other method of braking, which is plugging braking. Plugging braking is the method of braking that reverses the armature current suddenly by reversing the terminal of the source. Among the braking methods, plugging braking provides the fastest stop, but it can be harsh on both of the electrical and mechanical components. Plugging braking is the least commonly used method of braking, but it is appropriate for some applications. Plugging braking, sometimes referred to as reverse current braking. So, to bring the motor to a stop, the terminals of the source could be reversed. There are two things that we can calculate, which is the armature current using the formula IA1 equal to VT minus EA divided by RA, and the second thing is the reverse current using IA2 equal to VT plus EA divided by RA plus R. IA2, which is the reverse current, is typically designed to limit to twice the full load current of the motor. As soon as the armature stops, armature circuit must be opened, otherwise motor will begin to run in reverse. This is the graph of comparison of various braking techniques that contain plugging braking, dynamic braking, and coasting. The graph shows speed, time in seconds. Thank you for watching.